One of the difficulty that we have in the decision making is that we don't know which state of the nature will occur. Suppose there is a consultant that can say with 100% of the accuracy and can predict the future, and the consultant informs that 40% of the time the airport location is going to be on location A, therefore company is going to build on the hotel is going to build on location A, therefore the income is going to be $13 million, and if the consultant informs us that 60% of the time the airport will be at location B, therefore once we have the perfect information, we can the hotel chain is going to build in location B. As a result, the payoff will be $11. And if we consider this probabilities, then expected value with perfect information is going to be 0.4 times 13 million plus 0.6 times 11 million. That becomes $11.8 million. So if you remember in the previous slides, we talked that without the perfect information, the expected monetary value was 3.4. So the difference between these two values, the 11.8 and 3.8, is the value of the information that we got. So the difference between these two values is the expected value of perfect information, which is equal to expected value with perfect information minus the maximum of the expected monetary value. Also, all the times EV of the perfect information is equal to minimum of expected opportunity loss. So minimum of EOF is equal to expected value of perfect information, which is here. So this is another way that we can calculate EOL without converting all of the payouts to the regret. The next topic that we need to talk is about multi-stage decision problems. In reality, most of the problems that we have is we need to take multiple series. In reality, many problems involve a series of the decisions. For example, when you want to go out to eat a dinner, you have to make a decision about the location of the restaurant that you want to go, how much money you want to spend, and how you want to get there. So you have to make a series of the decisions in order to plan about going out and eating a dinner. So the same way that we address the single stage decision problems, we can use a decision tree to analyze a multi-stage decision problems. Consider this multi-stage decision problem. So we have a tech company that they are considering to apply a grant. The value of the grant is $85,000 and it's used in the communication technology. So the company, they need to spend $5,000 to prepare the proposal, and there is a chance of 50-50 that they get a grant. So if they receive the grant, then they need to make a decision whether they use microwave, cellular, or infrared communication technology. So the company has some estimation about the cost of the equipment that they need. For example, for the microwave, they need $4,000. For the cellular, they need $5,000, and for the infrared, they need $4,000. Now, once they have decided about this, there is a chance that the cost of the investment, the cost of the R&D research become a probabilistic, and they have some rough estimation. For example, the microwave has in the best case there is a probability of the 0.4 that the cost of the research and development is $30,000, and probability and at the worst case, which is the probability is 0.6, the cost of the research is going to be $60,000. The same for the cellular and infrared. Now, you can see there is two stages of the decision making. One is that whether they invest in the whether they should invest in the writing a grant, investing $5,000 to write a grant. So this is the first decision. And the second decision is what kind of the technology they can invest. So basically, if we want to represent this problem with the decision tree, we have something like this. So at the first, the company make a decision about whether to submit the proposal or not. So this is the first step of the decision making. The second one is that once the proposal is approved, so once the proposal is submitted, there is two case scenarios, two state of the nature. 50% the proposal will be rejected, and there is a 50% chance that the proposal will be accepted. Once the project is approved, there is another decision-making point. So the company needs to make a decision about what kind of a technology they can use. For example, microwave, cellular, or infrared. And then each of these decisions has risk. For example, if they invest on the microwave, there is a 60% of the high R&D cost and 40% of the low R&D cost. The same way for the cellular and infrared. So basically, if we consider this decision tree and the cost of investment, you can see if the grant is submitted, they have to spend $5,000, and then once they receive the grant, they will get $85,000. And then let's say the company goes with microwave, so they need to spend $4,000, and then again there is a 60% chance that they need to spend minus $60,000, and 40% they need to spend $30,000. Now, if you calculate for each of these, the same way that we calculate the payoff for a single stage decision making, we can apply the same technology, same techniques. Basically, by submitting a proposal, the company invests minus $5,000, and then when the proposal is approved, they get $85,000. So if we add up these two values, we get $80,000, and then if we select the microwave, the net profit so far becomes $76,000, and then by adding a minus $60,000 cost, the net payoff becomes $16,000. The same way $46,000 for this one. So up to here we have positive $76,000, and the cost of the R&D $30,000, then the payoff becomes $46,000. The same way you can calculate the expected value, calculate the payoff for each of the branches. Once we have these numbers, we can calculate the expected value, expected monetary value of each point of the decisions, each point of the event. So we have 60,000 times 60% plus 46,000 times 40%. So the payoff becomes expected monetary value of this branch, this event becomes 28,000. The same way for the second becomes 29,000, and the third one 32,000. So based on the maximization of the expected monetary value, this is the best branch that we can pick. So this branch is 32,000, so this is the best technology that we can pick. So at this point, the expected monetary becomes 32,000. Then the level of this point, which is the receiving grant, we have other branch that says not receiving grant. So comparing the expected monetary value at this point, which is minus 5,000 versus 32,000, then we have this value 32,000. So this is the 50% of the receiving 32,000 and 50% receiving minus 5,000. So once we get the expected value of these two branch, the expected monetary value at this point becomes $13,500, and then compared to this branch, which is 0, as a result, we follow all the way this branch. So we submit the proposal. If we not receive a grant, then we just lost $5,000. Otherwise, we are expecting to receive on average $32,000. So this is a way that we analyze the multi-stage decision-making problems. So we start with the lowest level of the branch. That means if this is the highest level, level 1, then we start with the lowest level, which is at this point we make the decision. We pick the branch that it has the highest expected monetary value, and then we move on to the next level. So this is the way that we analyze. The same way that we did analyze the sensitivity analysis for the single stage, we can do the same thing for the multi-stage decision-making problem. One of the techniques to analyze the decisions in the multi-stage decision-making problem is using a strategy table. So a strategy tables is analyze the effect of the two changes at the same time. For example, here we picked infrared as the best alternative. Now, what happens, we want to analyze when the chance of the high R&D costs and the receiving a grant change at the same time. So right now we have a 10%. Let's change this to 20%, and then we know that once this is 20%, the probability of the low R&D cost is going to be 80%. So this is automatically changed, and then the expected monetary value of this branch becomes 28,000. And then let's say the chance of the getting a grant is reduced from 50% to 20%. Then the expected monetary value of this branch becomes 1,800, and comparing to 0 is still high. So still, if we change this one to 10%, you can see when it is 10%, the expected value or expected monetary value is 0, minus 1,600. So we have to go with this branch, which is do not invest or do not submit the proposal. So here we want to analyze the effect of the change of each probability. And so one way is that to set up the strategy table, we need to use some if functions. For example, here we have to specify which technology is used. Basically, we have the expected monetary, and this expected monetary value is the maximum of the three branches. So if this value is equal to this value, it is microwave. If this value is equal to this, then it's cellular, and if this value that we have is the max of all three is equal to this value, then infrared. So you can write the nested if function. So if the value of this equal to this, then microwave. Otherwise, you can use another if function. If this value is equal to this, then it's cellular, otherwise infrared. So if you have a nested more than if you have more branch, you can again add nested if values and find this, or you can use a VLOOKUP and get the result. So the same way that we have here, you can select the branch. So this is, if this value is equal to this, then the item is 1, otherwise this branch. Now in the cell, once we have set up this, we can use the equation in the cell 11, the cellular 11. So if this value that we have here is equal to 1, then use the choose function, and the choose function, the input is Ch14, which is this value, and then this value that we have. If this value is, then we choose, otherwise B3 is not equal to 1, then we do not submit. So basically you can use the if function and update this value. So to run the strategy table, so here we pick the type of investment, and here we select whether branch 1 or 2. So you can write this using the if function, and then here we pick based on the result. So we use a if function. If function, if the investment is equal to 1, then we have to pick up which technology is that, otherwise we have the don't. So here we have the strategy that based on the probability of each of these values is determined. For example, for 20% and the 20% of the higher R&D cost and 50% of the receiving grant, the result is invest on the cellular, as you can see here. Now we just want to run the data, basically strategy table. So we select the entire table from the table that we wrote this equation, and then basically we select we consider the change of the probability of the higher R&D and the proposed probability of the grant. So to do this, we go to the data, what if analysis, and the data table. Now input table is for this row is this value, and for the column is the probability of the receiving grant. Once we have that, you can see that it doesn't matter what is the probability of the high R&D cost. All the time when the receiving grant, the probability associated with is equal or less than 0.1, the strategy is not investing, and then when the probability is more than 0.1, from 0.2 all the way to 0.1, the strategy for the less, when the probability of the high R&D is 0 or 0.1, the technology is infrared, and for the rest is cellular. We don't have microwave as a best strategy for none of the cases. Now consider another multi-stage decision problem. So this problem is about conducting a survey that the cost associated with survey is 0, then the result may come 67% favorable or 30% is unfavorable. Basically, this survey is about the new design of new car and favorability of this car among between the people in the market. So, for example, if the conduct survey, it doesn't have any cost, and there is a chance that the result becomes 67% favorable and 37% unfavorable. And based on this result, the company want to make a decision about whether build a large plant or a small one. So making a large plant has a $25 million cost, small one is $15 million cost. So for the same branch of favorable and unfavorable, we have the same costs here. Then if they build a large plant, then there is a chance that the demand is 90% high and there is a 10% low demand. The same way for the small plant, but when the outcome is unfavorable, 33% unfavorable, the high demand is going to be 30% chance and low demand has a 70% chance. So the same way that we we calculate the payoffs, we can calculate the payoffs for each of these methods. Here the story is a little bit different because we have the probability associated with each of these states, and then how we can basically calculate this. So here we later introduce a Bayes theory, but if we apply the same concept that we have learned so far, the expected monetary value of these two 90% times 150, 10% 70 becomes 142, and then again for this branch is 108, and then based on the maximum expected monetary value is building a large plant is most favorable. Now let's look at this branch. At this branch 150 and 70 is a payoff, and then when we get the expected monetary value, 94 is an expected monetary value for this event, and then for this event is 96, so the maximum of this is 96, so this is we have to make a small plant when the car is unfavorable, and then when we get the expected monetary value of these two is 126, so the expected result from this whole multi-stage decision-making problem is this value. Now here we can do a little bit investigate about the probability and how they can affect the result of this problem. So one of the ways that we can address is conditional probabilities that we will address in the next part.